In this section, we're going to be studying the hypothesis test for two proportions. The requirements for doing a hypothesis test for two proportions: number one, the sample proportions must be from a simple random sample and must be independent. And two, for each of the two samples, n times p has to be greater than or equal to 5, and n times q has to be greater than or equal to 5. That means there has to be at least 5 successes and 5 failures. The formula that we're going to be using to find the test statistic is as follows: z equals p sub 1 hat minus p sub 2 hat minus p sub 1 minus p sub 2 all over the square root of p bar q bar over n1 plus p bar q bar over n2, where p1 minus p2 is usually 0 because that's going to be assumed to be the null hypothesis. The p bar in the formula is calculated by adding the x values, x1 plus x2, divided by the n's, n1, n2, and then q bar will be 1 minus p bar. It's its complement. P sub 1 hat stands for the sample proportion for the first sample, x1 over n1, and p sub 2 hat stands for the second proportion for the second group, x2 over n2. Let's take a look at an example. Researchers reported results from studies conducted to determine whether people have different spending characteristics when they have larger bills, such as $20 bill, instead of smaller bills, such as $21 bills. In one of the trials they conducted, 89 undergraduate business students from 2 different colleges were randomly assigned to 2 different groups. In the dollar group, 46 subjects were given dollar bills. The quarter group consisted of 43 subjects given 4 quarters. All subjects from both groups were given a chance of keeping the money or buying gum or mints. The article includes the claim that money in large denomination is less likely to be spent relative to an equivalent amount in many smaller denominations. Let's test the claim using a 0.05 significance level with the following data from the study. So, in order to use our test statistic formula, we will need to calculate p1 hat, p2 hat, p bar, and q bar. So let's start with p1 hat. p1 hat will be x1 over n1. So in this case, that's 12 over 46, which to 3 decimal places is 0.261. p1, p2 hat will be 27 over 43, which when rounded to 3 decimal places is 0.628. We'll also need to calculate p bar, which is when you add x1 plus x2 over n1 plus n2. So in this case, that's 12 plus 27 over 46 plus 43. So when you calculate, remember to put these in parentheses, and then to 3 decimal places, you'll get 0.438. And then to calculate q bar, you'll take 1 minus 0.438, which is 0.562. So we probably should start by writing our hypothesis. Our claim is that people are more likely to spend money if they have the smaller denominations. So that's going to be our alternative hypothesis. So comparing P1 to P2, we think that the proportion of people that are spending is greater in group 2. So I'm using the less than symbol to write P1 minus P2. The null will always be when they're equal. So now let's calculate the test statistic. So using my formula from above, I want to subtract P1 hat minus P2 hat minus the difference in the proportions, which we are assuming to be 0, and then divided by the square root of p bar times q bar over n1, which is 46, plus p bar times q bar over n2, which is 43. So if you put that in your calculator, the test statistic is negative 3.49. So graphically, our test statistic is at negative 3.49. To find our p-value, since this is a less than, it's a left-tailed test, to calculate the p-value, we would do a norm CDF from negative infinity to negative 3.49. So using your calculator, you would do second bars norm CDF from negative infinity to negative 3.49, and you get a p-value of 2.42 times 10 to the negative 4. That's 0.000242. So it's a very small p-value. So our p-value is less than alpha. If the p is low, the null must go. So we reject the null. The null hypothesis is that they're equal, and I'm rejecting that. So I'm supporting my claim that there is a difference. In fact, I think that the proportion of people who spend the money is less in the group where they're given the larger dollar bills. So support the claim that the proportion who spend is greater in group 2. Okay? This test can also be performed using the 2-prop-z test on your graphing calculator. So let's take a look at how that would go. You would go to Stats, over to Tests, and down to a 2-prop-z test. 2-prop-z test. And then you'll enter in x1, which is 12, n1 is 46, x2 is 27, and n2 is 43. Our confidence level, since it's a 0.05 significance level, oh sorry, I did a 2-prop-z end, my mistake. We want a 2-prop-z test. Okay, so entered them in. So this is a less than test, so I want to select less than, and then calculate. So you can see that my test statistic is negative 3.487, which when rounded to 3 significant digits is the negative 3.49. And my p-value is 2.44 times 10 to the negative 3, which is 0.000244, which is really close to the p-value that we calculated. It's a little bit different because of rounding, but you can always do the 2-prop-z test to find your test statistic and your p-value, and then decide if you want to reject or fail to reject the null. Now, let's take a look at how you could create a confidence interval for the difference between the proportions. The confidence interval takes the difference in the proportions minus the margin of error, and the difference in the proportions plus the margin of error. So there's a typo here, it should be plus. And that's to estimate the difference in the two population proportions. The margin of error is calculated by z sub alpha over 2 times the square root of p1 hat q1 hat over n, 1 plus p2 hat q2 hat over n2. We typically will round to 3 significant digits. So let's take a look at the same example, but this time create a confidence interval. Example 2. Use the sample data given in example 1 to construct a 90% confidence interval estimate of the difference between the two proportions. So this is going to be a one-tailed hypothesis test. So graphically, if 0.05 is in one tail, since it's a confidence interval, there's also 0.05 in this tail, so that's a 90% confidence interval. So we are going to be creating a 90% confidence interval. They want to know, what does this suggest about the claim that money in large denominations is less likely to be spent relative to an equivalent amount in many smaller denominations. So let's calculate the margin of error by hand. So the formula for the margin of error is the z sub alpha over 2, which for a 90% confidence level, z sub alpha over 2 is 1.645. You can get that from the table. And then p1 hat is 0.261, and you need q1 hat. So if p1 hat is 0.261, then q1 hat will be 1 minus that, which is 0.739. And all of that is over n1, which was 46, plus p2 hat, which was 0.628. And so if P2 hat is 0.628, then Q2 hat will be 1 minus that, which is 0.372. All of that is over N2, which is 43. And if you calculate that, you will get a margin of error of 0.161. So to create a confidence interval, we want to subtract P1 hat minus P2 hat minus our margin of error. And then on the other side, do P1 hat minus P2 hat plus our margin of error. So in our case, we would take 0.261 minus 0.628 minus our margin of error, and 0.261 minus 0.628 plus our margin of error. And that will tell us that our estimated difference between our proportions is from negative 0.528 to a negative 0.206. Since 0 is not in our confidence interval, that means that there is a difference. If 0 was in here, then that would mean that they're equal. So there is a difference. So there is a difference in the proportions. In fact, we think that 53 to 21% fewer people will spend the money given the larger denominations. So we are 90% confident that the proportion of people who spend the money will be 53% to 21%, rounding, less in group 1. Okay, so this can also be done on the calculator doing a 2-prop z-int. And again, you'll have to put in your x1, n1, x2, n2. And in this case, we wanted a 90% confidence level. So that's going to be 12, 46, 27, and 43. And on your calculators, if you've already entered those into your 2-prop z-test, they will stay there for your 2-prop z-int. 2-prop z-int. My numbers are already there. I just need to make sure that it has a confidence level of 90%. And then calculate. And you'll see that my values are negative 5.28 to negative 2.06 when rounded to 3 decimal places. So again, that supports that they're different and that the people with larger denominations are less likely to spend.